Introduction. Goals of the lab. To determine the pressure drag coefficient of a circular cylinder using discrete pressure measurements on the surface. Evaluate the effects of Reynolds number and surface roughness, tripping the boundary layer on the results. Contemplate sources of uncertainty and error in a more complex test. Undertake flow visualization that has qualitative and quantitative value. For airflow past a circular cylinder, the drag at moderate or high Reynolds numbers is primarily the pressure drag. This occurs because at these Reynolds numbers, the boundary layer separates from the cylinder surface and the resulting pressure around the cylinder is no longer symmetric at any instant and features significant low pressure in the wake. However, the flow separation can be delayed and the pressure drag reduced by generating turbulence in the boundary layer to keep it energized and attached as long as possible. This phenomenon is what we are observing and trying to simulate. Before starting the experiment, all standard safety protocols were taken. All the exit doors were closed and a flashing alarm was placed outside so that the public knew that the wind tunnel was active. A wind tunnel supervisor was also present to make sure everything was done correctly and answer any questions. Initial pressure and temperature were recorded before the start of the experiment in order to calculate the initial air density. Next, the cylinder was checked for correct dimensions and that it was properly positioned in the tunnel. Floodlights and a laser were used to illuminate the smoke near the cylinder, revealing vortices as they were shed. A phone camera was used to record the flow of the smoke above and below the cylinder. In addition, the camera was used to capture slow-motion video of vortex shedding across the cylinder. Lastly, a total of 24 evenly spaced static ports were used to measure the pressure distribution around the cylinder, and pressure values were uploaded to MATLAB and used to calculate velocity and pressure. Furthermore, LabView was used to determine the flow velocity in the test section through the pedostatic reading. Any possible sources of error were noted and photographed to be reviewed in the case of unusual data.
2 separate test runs were used for this experiment, cylinder without trip and cylinder with trip. Within each test run, there were 3 different RPM speeds of 150, 300, and 650 RPMs. The sampling rate was varied for each RPM setting, with data taken at periods of 100, 300, and 500 microseconds. At each sampling rate and RPM setting, 3 trials were conducted. This gave us a total of 27 sets of data for the cylinder without trip and 27 sets of data for the cylinder with trip. After every RPM increment, LabView was used to observe the change of velocity, ensuring that the wind tunnel reached a steady state before recording the data. In addition, a video of the flow at each RPM setting was recorded in real time and in slow motion in order to use the results for later. After all the data was collected, the wind tunnel was slowed down and then turned off. For the experiment, we tested pressures for the untripped and tripped cylinders. For the untripped cylinder, the flow separated around 75 degrees from the front of the cylinder at all RPMs. We placed the trip slip 15 degrees to the front of the top and bottom of the cylinder, which turned out to be right where the flow separated according to our data. For the trip cylinder, the flow separated at 300 and 600 RPMs at around 120 degrees from the front of the cylinder. However, the 150 RPM with the trip strip did not affect the angle of the flow separation, and we got around the same angle as the untripped, around 60 degrees. We also found that around 240 degrees, which corresponded to port 6, to be reading unrealistic data, so we assumed that the port was broken. To account for the faulty port's error, we averaged the adjacent port's pressure. Drag was calculated using the readings from the 24 static pressure ports distributed around the cylinder's circumference. To determine which pressure port was at an angle 0, meaning directly facing the airflow, the pressure readings from each static port were compared to the readings from the pitot tube in the tunnel. Port 12's reading best matched the pitot tube's readings, so port 12 was considered to be at angle 0, and the rest of the port's angles were to be determined based on this assumption. The average coefficient of the drag was calculated for each trial based on the average drag and average free stream velocity for that trial. The drag coefficient was found using the equation CD equals 2D over rho v squared A, where rho was measured density of the air surrounding the wind tunnel and A was the total surface area of the cylinder.
Interestingly, the drag coefficient of the untripped cylinder decreased as velocity increased. However, for the tripped cylinder, the coefficient of drag decreased dramatically from 5 meters per second to 11 meters per second, then increased slightly at 25 meters per second. The sampling period did not have a significant effect on the coefficient of drag versus velocity plot. This is likely because the coefficient of drag was calculated from the time average drag. Time averaging likely overcame errors related to lower sampling rates. To better understand which portions of the cylinder contributed most to drag, we created polar and rectangular plots of the drag contribution at each point around the cylinder. Predictably, pressure drag peaked at the front and back of the cylinder, and the total drag in the rear was generally greater than the total drag in the front. Interestingly, certain parts of the cylinder actually had negative contributions to drag. Starting at about 30 degrees and ending at about 90 degrees above and below the front of the cylinder, drag contributions became negative, meaning these sections of the cylinder experienced a pull towards the free stream. This likely resulted from Bernoulli's effect. Air hitting the face of the cylinder rapidly accelerates as it tried to get around the cylinder face, and the fast-moving air created a low-pressure zone in small sections at the top and bottom of the front half of the cylinder. At 150 RPMs, the tripped and untripped trials had nearly identical drag profiles. At the higher RPM settings, 300 RPM and 650 RPM, there were significant differences between the tripped and untripped drag profiles. Although the pressure drag at the front and back of the cylinder matched closely for the tripped and untripped trials at higher RPMs, the negative drag components at the top and bottom of the front half of the cylinder were much larger for the tripped trials than the untripped trials. This suggests that tripping the flow to become turbulent resulted in more fast-moving air near the top and bottom of the front half of the cylinder. This conclusion is consistent with the prediction that tripping the flow would delay separation. Plotting the individual pressure readings at each angle around the cylinder revealed interesting patterns in the data. Pressure versus angle was plotted as it changed with time for a given trial. At low RPMs, the pressure at each angle was similar for the tripped and untripped trials. However, at higher RPMs, the pressure near the top and bottom of the cylinder's front face was much more negative for tripped trials than untripped trials. The largest pressure differences between tripped and untripped trials occurred nearing the observed point of flow separation, predictably. For tripped trials, the flow likely became turbulent as it reached these points, and the turbulence delayed separation. The fast-moving, turbulent flow at these points created low pressure, consistent with Bernoulli's principle. On the other hand, in tripped trials, boundary layers built and flow separated around these points, reducing the speed of flow over the surface and diminishing the magnitude of low pressure at these points. This video also clearly reveals that the port corresponding to an offset of 240 degrees from the front of the cylinder gave bad data. The data here sharply dipped compared to the data from the ports near it, and this trend was present in all trials. Note that the pressure at 240 degrees was negative, so on polar plots, the pressure appears to coincide with an angle of 60 degrees. There are several possible explanations for this dent in the data. Most likely the port was faulty. Another possibility is that there was a physical disturbance of the flow near this port, such as an abrasion on the surface of the cylinder. Interference by the trip strip can also be ruled out as the source of the error, since the error was present in untripped and tripped trials as well. In any case, there was clearly some sort of systemic error at this point. If we had a ball instead of a cylinder in there, would the behavior be different with roughness, Reynolds number, asymmetry, etc.? Since the World Series is currently taking place, it would be fitting to use a baseball as an example. The stitches on a baseball give it a relatively rough surface. The stitches would disturb the boundary layer, like the trip strips on the cylinder, moving the boundary layer further along the baseball's surface, decreasing the size of the wake in the process. If the wind tunnel is running at about 25 meters per second, the baseball would have a Reynolds number of about 1.4 times 10 to the fifth compared to the cylinder at about 3.14 times 10 to the fifth. Its low Reynolds number indicates that the baseball would experience laminar flow. It's preferred to have the baseball experience laminar flow because pitchers need to have a clear understanding of how the ball would react with different pitches. If it would experience turbulent flow, then the pitches would be unpredictable, negatively affecting the pitcher's team. The picture below is a good demonstration of what occurs with a baseball.
When comparing our coefficient of pressure graphs with our Reynolds number graph, we can observe an interesting relationship. Approximately around 400,000 Reynolds number, the flow starts to transition from being laminar into turbulent flow.